Hi, and welcome to this talk about the how and why of reinventing the wheel. I'm Alan, and I'm giving this talk with Ryan Fleury. Uh, this phrase "reinventing the wheel" is usually used as a sort of deterrent from uh, exploring ideas that have already been figured out, wasting time on that. But one thing that we really like, Ryan and I, about the handmade community is the fact that it is a place where we are sort of more encouraged to explore established ideas, and we've been working on a project that we are going to show you that has involved us breaking down a pretty fundamental wheel of how we program, and that's the tools, the glue that we use to put together the tools for programming. So we're going to show you what we've been doing, and we're going to start by looking at the the sort of history of programming tools. So programming tools started when it was just circuit boards. The physical arrangement of circuits create a particular device with particular behavior, and rearranging those circuits created different devices. But it didn't stay that way. Sort of computing began for real when the idea of encoding the description of a program came along, and we started that kind of stuff with things like punch cards. In punch cards, you describe your program with a sort of series of lines and put each line of text onto a card, and then stacks of cards would represent programs. And the limitations of what you could do were expanded, because now instead of physically arranging circuits to create each new device, you could have just one computer device that you could then run lots of different programs on. But obviously, this was still quite limited. The size of the stack you could feed into the devices, the size of the boxes holding the cards, the speed with which you could iterate on the programs were all limited by this. So eventually, this idea of the software really took off when we got rid of the physical encodings altogether, and we just described the programs as digital files. So, the medium of programming started off as a physical circuit, and it evolved to this point of there being a digital file with a digital description of what needs to happen. And then, the ideas of compilers and stuff have been around since then. So that's sort of, how we got from circuit boards to a very early version of software. And if you think about it, what we're doing now, we have much larger boundaries in which we can work. We can make much larger programs than before. But the basic concept hasn't evolved again since then. We still have lines of code that get interpreted into programs and then run. Of course, we are thinking about the ways we're going to make better tools and questioning if this is the way it should stay forever. And we're not the only ones questioning that. This is an idea that gets explored by a lot of people. And, here are a few examples. There's, ideas like Scratch or Unreal, which, have carved out a real niche, whether it be educational or sort of game logic scripting with blueprints. This is also not a new idea. This goes back, all the way to 1979 in this picture, and possibly even before that, with things like VisiCalc, which is a precursor to Excel, but it's still a way that lets you organize computation and get the computer to compute functions for you to, do work for you. There's also modern research in making real editors that could actually maybe potentially replace our programming tools, and how to do that. And that we have a screenshot of Hazel, which is an academic research project trying to do that. But the thing is that none of these have really taken over like text files did when they took over punched cards, and when punched cards took over physical circuits. So we are interested in what would it take to actually do another full replacement of the current system. How could we push that boundary further? And our idea is we need to be careful not to change too many concepts at the same time. If you look at what happened in the transition from punched cards to digitally stored software, they didn't change the compilers or the concept of what you put into a program. They just changed the medium that was used for editing and storing the program. And they kept as much as they could the same along the way in that transition. And we think that a lot of these other things that have been tried don't take over because they stray too far at once, and they just can't get everything exactly right when they're changing that much stuff. So we've been working on our version of a possible replacement, and Ryan's going to show you a little bit of what that looks like.
So, as Alan mentioned, we've been working on a solution to what we think are some problems with existing tools that we have. And we've been working on it for about 7 or 8 months at this point. This is the program that we've been working on. And I can go ahead and open up some code just to show you really quickly, and then we'll keep revisiting this program throughout the talk. But I'll go ahead and open some code here. Just brings up this kind of normal file explorer. And when I open up the demo code that we've prepared, you'll see that it's actually not that different from maybe systems that you're used to. So we have procedures, structures. It looks a little bit like a C-like language. Not identical syntax, but hopefully it feels pretty familiar. I have my cursor. I can select things. It feels a little bit like a text editor. Though something that's important to note is that the representation that's actually storing all of this code is much different than a text file. But to give you a quick demo of actually writing some code, I can go ahead and write a little hello world program here. I'll just type hello Handmade Seattle, just to prove that everything's actually working. And I can go ahead and build like this, and I can run the program that was just built here. So you can see I get the output that I just wrote in, and that's basically how it works. So it feels pretty similar to maybe systems that you're used to. Something that I can demo really quick here is introducing an error. So there's this v4 constructor, which just makes one of these vector 4D structs here. And what I can do is if I remove the return type, we'll see that some red lines appear, suggesting that some errors have been introduced into the program. So it's telling me that this procedure needs a return type. Additionally, if I go to any of the usage sites of this function, there's going to be an error because I've removed the return type. And that brings us to the next topic we are going to talk about, which has to do with error conditions. So I'm going to pass it back to Alan, and he will talk about that with you.
All right, so we're going to go through this whole talk looking at one problem at a time. And as Ryan just said, the first problem we're going to look at is how we deal with errors in our system. So first, we're going to look at how we are dealing with errors in the current system, because again, the idea is to not go too fast and too far away from what already works, but to try to fix some key issues along the way as we're, doing this experiment. So here we have on the slide, if you look at the red arrow on the left-hand side at line 15, there's a brace that's been dropped out. And on the right-hand side, you can see these are screenshots of Visual Studio, and Visual Studio is saying that the error it has detected is on line 24. But of course, I think you can tell pretty easily by looking at this code that the real place where the error got introduced was on line 15, and Visual Studio just doesn't have any way of getting that right. It's kind of a problem with how parsing works, and because we're relying on files that are text files that have to be parsed, there's no perfect way for it to solve this problem. But that isn't the end of the story. This problem creates more problems. So once it has a sort of, maybe we'll call it a catastrophic error, that it just doesn't know what actually went wrong and it can't recover, it also doesn't have the ability to report other weird things. So here we have some code that's clearly an error. There aren't any variables called B, C, or D in the scope. You can't assign a string to a struct like that, and it just doesn't know any of that is wrong because it can't get any good information about what the rest of the code looks like. If we look for Visual Studio's recommendations on how to fix it, they don't make any sense either. It thinks that maybe the problem is that this is a declaration of a function that didn't get a semicolon. But of course, again, this is just not the right idea, and we can't really blame Visual Studio. Despite all the work you might put into it, there's just no way you could have done this exactly right. You could have added more heuristics and stuff and done a lot of effort to think, oh, maybe if you find a comment with a closed brace, or if you find that the indentation suggests a different scoping than what the braces actually give you, that maybe you could recover. But if you actually look at the problem, it's pretty unreasonable to expect something much better than this. Another way we could show the same kind of problem is that in our current system, if I introduce an error by putting a typo on the name of something, like this node struct, then it thinks that the errors are everywhere else in the program, right? and there's just no way for it to know any better. In general, the way we kind of like to think about this problem is that when compilers were first designed, they were sort of in charge of creating an error handling strategy, and they created the error handling strategy of text comes in, and if it doesn't form a good program, a syntactically and semantically correct program, then errors get reported. But that's a fairly slow cycle of when that error comes back to the rest of the system. And now when we're trying to make things like text editors that also know when errors are happening, or any other system that needs to deal with errors, that strategy isn't good enough for those other tools outside of the compiler. So what can we do about this? One thing that a lot of tools in this area have explored is this idea that we write an editor that prevents errors from ever occurring. Here we have a picture of Scratch, and if you work with Scratch, the basic concept is that you can create incomplete programs with holes in them, but you can never put two pieces together that don't fit. So your programs can be unfinished, but they can never have errors that would be like compilation errors besides those specific incomplete parts. A more developed version of this idea in Hazel is the idea of typed holes, where you build a language that specifically has a construct in it called a hole that type checks in certain ways, and a special editor for that language that makes sure that the program you're writing always type checks. Early on, we leaned this way too, and over time we came to feel like there's just sort of bigger problems with it. And without going into the theory why, it just turns out that having errors is pretty useful sometimes for a lot of different parts of the system. So the good news is there's another way. We think that this idea of containing errors with the structure of the medium is better. And what I mean by that is, I think, best described by looking at an example in Excel. So here we have a sort of a spreadsheet it's got a table of numbers and it's doing some sums on them. I can show you it's doing a sum of each column, and then it takes the sum of the subtotals there. And so we have various computations happening. Now, the cool thing about the system is that if I introduce an error to one of those subtotals, then I will get errors reported, but you can see on the column for concept C, that column can still get a correct sum. The error in one cell is contained and it doesn't catastrophically affect the computation in the rest of the system. And our experiments have led us to think that it's possible that we could do something very much like this with a C-like programming system, and that is a much more useful way to deal with errors. And Ryan's going to show you more about that error system next.
All right, so I am back in the program, and what I'm going to do to show you that how error containment in the system works. First, I should probably fix up this error that I introduced before on this v4 constructor, and then I can go down to these two entry points here. So you can see I have two programs here, one of which is this entry compare RGBA HSVA function, which is going to take some RGBA vectors, convert them to HSVA, and then print out the results. So I can actually build this function here, and then I can show you that this output is produced here. I can also change, one of these RGBA values or whatever, and we get different output. That's all fine. And then this function down here is a different program which just prints out a vector. So even simpler program where I can build and then run it, and we'll just see that we get the vector that we've formed inside of the program. We see that is printed out here. Now, something to note about these two functions is that this entry compare RGBA HSVA function calls this HSVA from RGBA function. That's the function we wrote to convert an RGBA vector into an HSVA vector. The entry print vector function does not call HSVA from RGBA. So to demo error containment, what I can do is go to that HSVA from RGBA function, and I'm just going to introduce an error. Simple way to do that, take off the return type, right? That doesn't make any sense to the system. If I wanted to say that no return, there wasn't going to be a return value, I would have typed void. But in this case, I'm going to take it off, produce an error. You'll see that this part, the name of the function is telling me, hey, the procedure is going to need a return type. And we'll see that errors propagate throughout the system when it's relevant. So we'll see that the expression does not assign to the return type here. When I try to return a vector 4D, it doesn't make any sense because the return type isn't defined as a vector 4D. Additionally, all the call sites are broken too, so we're back at that entry compare RGBA HSVA function, and we'll see that these three statements here, or these three declarations, are broken now. So I can't build this function. If I try, it's just not going to work. I'm going to get an error. But the entry print vector function is actually still going to be just fine. So I can build that. You'll see that it still works, and I can still produce output with it. So that's a pretty good example of how this system localizes errors to the trees of code in which they're relevant. So if I didn't call a function that was broken inside of a program, it just doesn't matter. The error is not relevant to the thing that I'm trying to do. And to talk a little bit more about how this all works, first I want to introduce to you the model that we've drawn up here of the existing system that you or me will work in when we're working with C or C++. So we use our editor to produce text files in the system. It gets tokenized and parsed to form an abstract syntax tree. And hopefully what you can appreciate is that text is kind of like the least structured part of the pipeline. Over time, the compiler is going to gain more structure and eventually produce an abstract syntax tree and then type information. And then, of course, code gen happens and everything. And what we're sort of proposing to do here is just start later in the pipeline. So in Dion, our format is much closer to what an abstract syntax tree is. And that has many benefits, and we'll get to many in this talk. But specifically when it comes to the subject of error handling, the important thing to appreciate about an abstract syntax tree or something like it is that it's a tree, right? And inside of an abstract syntax tree, the boundaries of groups of code are very clear. Unlike in text, when it's just kind of a big soup of characters, you're not really sure where something is supposed to start or end. So in this diagram here, you can see that we've introduced an error, which is represented by that red X. And the thing about that red X is we don't even need to necessarily let it spread to its siblings or to its children or its grandchildren. We can actually reason about it and how far it goes in the system in a much more well-defined way. And that's kind of only the beginning. We have plenty of other things to get to. So I've put a list of 4 on the screen here. We want to experiment with incrementally building error information to make sure that user feedback is always instantaneous. Additionally, there's no reason why we should be the ones in charge of defining all the errors extensively that you would ever want. So, maybe the user should be able to define their own errors, for example, house rules in a code base or something. Those should be possible. Because also we can tie errors much more closely to the semantic structure of the program, and that's what the user is editing, we can also have a much cleaner path to suggesting automatic or recommended error fix-ups, which can, for example, if you're referencing something that doesn't exist, maybe it suggests that you add a declaration, maybe gives you a fast path like a hotkey or something to add a declaration and then reference it and make sure that that declaration matches the type of the expression that you're in or something like that. There's lots of options there. Additionally, errors are only one way of sending the user information. There's also plenty of others too, like warnings, notes, and to-dos. Maybe to-dos expire into warnings, warnings expire into errors. There's just lots of possibilities here, and we've kind of only scratched the surface. So now I'm going to pass it back to Alan, and he will tell you about the next problem we're going to explore.
Okay, so we're going to move on to a new class of problems now, which is sort of the class of problems that arise out of tools besides the compiler that need to get access to structure and pattern in the codes, or in the code you write. So I think the very basic example of this is variable renaming, right? It's something that the compiler, eventually after doing all the parsing, it has all of this information about how things link up. And as a programmer, sometimes you just want to say, like, I'm renaming this concept. It shouldn't be complicated. It's just anything that needs to get linked up to this name, I want it all to change at once. But actually implementing that in an editor, it turns out, is more difficult than you would think. Even in the simple case, you can't just do a string replace because that string could appear in multiple places. In this case, we're looking at renaming X, but there's, X's that maybe you didn't mean to rename, especially the X in the word max. That one you probably definitely don't want to rename. So your tools end up needing to do extra work to actually provide a feature like this. They either have to go the route of making really good heuristics that tend to give you the right thing. Or I think in the case of Visual Studio, it tries to constantly in the background be parsing and type analyzing everything so that it can give you higher level control over the code. But of course, that is a lot of work for them to write the code that does that, and the computer has to be doing a lot of work to keep that system up to date. There's all kinds of problems involved in that. And this is kind of just the easy example. If we look at harder examples, we can actually get to the point where neither heuristics nor type checking can solve the problem. So here's two structs that share some names in their members, right? A two-dimensional point and a three-dimensional point. They both have a member named X. And imagine I was going to go and rename the P2 X to be something else for some reason. Okay, so if I'm in that situation, you can see, just looking at the highlights here, that there are several different places where the identifier alone just looks like the same thing. So a string matching heuristic would have to be a little bit smarter at least and know what the difference is between an X that does and doesn't have an accessor token to the left side of it, right? But that wouldn't be enough either, because there are multiple places where an X is going to show up, but it's on the wrong type. So all of the X's that are for P3s will be accidentally, brought in for renaming along with the X's for P2s or vice versa, right? You have to be able to differentiate if you really want this sort of feature to work. So you would need to be able to actually figure out what is the expression on the left-hand side of the accessor and what is the type of that expression. And then you could start to build a feature like this. So maybe that is an argument in favor of we should always be doing this, type checking in the background for these editors to make these features work, right? Well, it turns out there's also an example where the same thing won't work, and a heuristic might have been a little better, which is in a language like C or C++, where you can use a preprocessor to hide some code. There's no way for a correct parser and type checker to actually get at the code inside of an if0 like this. And yet, if you were doing a rename of all of the X's in P3, well, you'd kind of want it to be the case that if you ever re-enable this code path, that variable renaming was applied inside the code that was dead at the time, right? And this is in a part a language design problem, but we don't necessarily think it should be a language design problem. These are editor features, and the fact that if you want to make some of these features work better, you have to constrain the language design kind of feels like a flaw of the system overall. So this isn't the only kind of problem that has, or this isn't the only kind of feature that you want to write that has these problems. Simply making something like a dot lister, like we have here, also needs that type info. And in this case, it needs type info that you get back even when the program doesn't actually parse. So it has to rely on forgiving parses and do other tricks to still figure out the type of the expression on the left side of the accessor. Same thing again with function calls. It doesn't necessarily actually type check, but you want to be able to get type info back from this sort of situation so that you can display function signatures. Even something as simple as go to definition breaks down if you push on it, so that either the type checker version can't find the thing it's supposed to because it isn't loaded in, or it's hidden in some way by the build settings, or the heuristic doesn't know which of several options is the one to actually jump to. And so, this is kind of a hard problem in the current system. So what can we do about this? Well, in this case, the answer isn't very complicated. The entire point is to switch the structure. And so the idea is, while we're switching the structure, let's just make sure we use the right structure for the problem that we're trying to solve. And so we think we've done a little bit to push us in that direction with our project. And Ryan's going to show you now what our results look like.
So Alan talked about a few of these problems, the first of which is renaming. So if I come to that function that I showed you earlier of this HSVA from RGBA, or the HSVA from RGBA conversion function, in here we have this member variable, or not member variable, a parameter to the function called RGBA here. And you can see it's used pretty extensively throughout this function. And the interesting thing about using an abstract syntax tree for this is that the way that the system knows that, for example, this usage site is talking about this RGBA variable is not because the same string is used in two places. We're actually able to encode this relationship at a much more structural level, so that you can think of it more or less as a pointer coming from this to this declaration. That's not exactly what it is, but you can think of it that way. And what that means is that if I came up to this RGBA variable declaration, I can just start renaming it, and it'll update across the entire function. All usage sites just automatically update. There's no heuristic. It's deterministic, and I can rename it whatever I want, really, and all the usage sites will just automatically update. And additionally, it's true for members of structs too. So I could come up to this vector4d struct definition and just rename this test x, for example. And you can see it updated in this v4 constructor already, and everywhere inside of this hsva from RGBA function. It's also updated, and nothing special really had to happen there. So for example, Alan went over some cases where you would need type information to do this correctly. This is one of the features inside of Dion where we actually don't need type information. All we need is a stronger encoding of what it means for something to reference something else. Another thing that Alan talked about that required type information in a textual editor, for example, but inside of Dion doesn't require type information, is go to definition, right? So if you're at some usage site of something and you just want to go to the definition of whatever's being referenced, we can go ahead and demo that in Dion here by right-clicking the reference and then just hitting go to definition. It'll take us right to the definition. It also works with members, for example, so I could come to this test x that I renamed and just go to definition. It's going to take me to the declaration of test x, and that didn't require type information, but some things do require type information. So two examples of that are the ones that Alan went over with you, which are seeing what's in a struct from a usage site if you're trying to access the struct with like a dot operator, and also seeing what parameters a function takes. So I can demo that here. I'll just make a quick struct here. And I'm just going to have a few members inside of it. So I'll just make an x, y, x, y, and z here. And if I make an object of this type, I'll just call it foo. I'll reference the struct here. And I could start talking about the members of this struct just by typing foo dot, and then I can actually get a list of all the members just at the call site. And that's actually using type information. So this is one of the things where we still require type information, but it's actually much easier to get to the type information from the structure of the code. Whereas when you're starting all the way back from text, it's much harder to get to the proper type information. And similarly with function calls, it's the same idea. So if I wanted to call this HSVA from RGBA function, I could type the name here, and then I could use this open paren, and it's going to just automatically fill out the parameters that are actually proper for the function or for a call site of the function. And I don't have to rely on that. I could also type my cool RGBA here and just get a list of all the parameters that the function is expecting from the call site. And that's, again, because it's much easier to get to type information within this system than it is from within text. So that's kind of how it works inside of Dion right now. And to provide a little bit more insight into why we think this is such a significant benefit, I want to bring to your attention on the left-hand side of this slide, I have a list of all the tools that you probably work with all the time. So we have compilers, editors, version control, debuggers, static analyzers, metaprograms, and we touch those always. What we can sort of think of all these programs as doing is trying to get to code smartness to some degree. Some of them don't really try at all, like version control, but compilers obviously have to try really hard to get from the left-hand side, where the blue line, where everybody starts, to the right-hand side, the green line, where it's the best possible code smartness you could ever imagine, right? And Alan's already shown you a few cases where the compiler falls short. Editors fall short also for some of the reasons that Alan has already raised. Version control just doesn't try. All these things do a lot of work to get to best possible code smartness. They all sort of end up falling short. Additionally, debuggers, you can imagine them having to parse expressions inside of a watch window or something. Everybody's having to do this work, and everybody kind of falls a little bit short. And what we're suggesting with Dion is to just not start from the left-hand side of the screen completely, and instead shifting the blue line a little bit closer to the best possible code smartness. And hopefully what can be appreciated from this from this action within this model is that we're cutting out a lot of redundant work from all of the tools. So compilers, for example, wouldn't have to do a parse and form an abstract syntax tree. Editors don't have to do an incremental parse, which is even more difficult. Additionally, they don't have to rely on heuristics for things that feel like they should be well defined. And instead, everybody's starting from the same base level of structure and code smartness. And hopefully what can also be appreciated is that that also cuts out not only a lot of duplicated work that basically everybody has to do, but it also cuts out a lot of options for bugs or inconsistencies between the implementations of the things that everybody's having to implement, which are all pretty complicated. It's always super frustrating, for example, when the parser inside of my editor doesn't agree with the parser that my compiler uses. So my editor's telling me that there's an error, but my compiler doesn't tell me that that error is there. It all gets really frustrating, and even if both implementations aren't bug ridden, that feels like a bug to the user. So it kind of just adds all of the bugs and inconsistencies together, and what we're suggesting with Dion is to just take all of that work out and start everybody from some base level of code smartness. And just like the previous section, there's plenty of problems remaining left to study. How do we share code, right? Everybody shares their code through something like GitHub. That's a problem that we have to address. How do you share code in general, right? How do I send a block of code to my friend? And a more subtle problem is, what replaces the idea of file and line coordinates? If I'm trying to tell somebody to go look at a particular location in a code base, how do I tell them to that? Do I have some kind of way to give them some coordinates? It's going to look different than just a simple file and line coordinate system. And additionally, there's plenty of other potential implicit systems that we need to replace that sort of exist at the intersection of all these tools, and we haven't solved all the problems yet. So there's still a lot more to solve. So I'm going to pass it back off to Alan, and we're going to move on to some other problems that we have solved.
All right, so a quick recap. We've looked at two problems so far, and these are the problems of the error strategy for our compute system and this problem of putting our code at the right level of structure to make the tools easier to create, right? This next problem is another one we've had a chance to explore, which is exemplified by tabs versus spaces. But I want to give you an idea of what the general point of the problem that we're trying to get at is here, which is the sort of things where you are forced by the systems you use to make decisions that feel like they should be irrelevant, but that for one reason or another you are forced to choose anyway, and in some ways they actually do become important. So tabs versus spaces, clearly it feels irrelevant to anyone who only cares about the quality of the software that gets produced out the other side, but you have to choose what you're going to do, right? It doesn't actually just stop there. The entire problem of styling takes up a lot of effort for people like people implementing editors like Visual Studio. So here what we have is a screenshot of all the options Visual Studio gives you to decide where your braces get placed, how the indentation is handled, does it use tabs or spaces, how many spaces, if it is using spaces, all that kind of stuff has to be managed by this editor. But of course, Visual Studio isn't the only editor. Here's Vim doing the exact same thing again in a slightly different way, giving a bunch of options for how the code is going to be styled by the automatic indentation. Of course, editors aren't the only thing. There are also languages that come with automatic formatters, because this is a problem that apparently we're putting real effort into solving, even though it feels like it should be irrelevant to the software we generate. We are forced by the current system to deal with style. And, these problems get more serious than just style, too. So another version of the same kind of thing is choosing how to organize your code. Here, what I have on the screen is an example of two ways to organize the same thing. This is like a sketch of a physics system, and there's a couple of constants that control the behavior of the physics system. And you kind of have two choices when you have a bunch of constants about how you're going to organize them. You could organize all of the constants together at the top of your code file or on a header or something, so that there's one spot where you go to tweak and tune the system by just changing the knobs, the constants that you set up initially. But sometimes when you're editing code, you're also going to want to know, what is the value of this constant so that I have a mental model for its range. Or you're going to look at a constant and go, how exactly does that constant affect the system? I need to go read the code that uses it. And so in cases where you care a little bit more about the details of how the system works and less about the tuning, it's more convenient probably if you organize the constants like the picture on the right hand side, right, where the constants are nearer where they're actually getting used. But the problem is it's pretty hard if you sit down to work on this to come up with a system that really consistently lets you choose the organization on the fly for the problem that you're working with day to day. You generally have to pick one way or the other to organize the code, and that defines the workflow you will always end up living with in that particular code. But it gets even worse than just how you organize your code, because sometimes these decisions about organization are coupled to the code that actually gets generated. So we think switches versus vtables is another example of this kind of problem, and we think it's a pretty serious version. But first, we're going to take a minute to try to convince you that switches and vtables are two alternative ways to organize the same basic concept in your code. So imagine you're creating sort of a little game which has an entity system where each entity needs to do an update and a draw on each frame, and there are different types of entities like a player and a power-up and a wall, like I have on this diagram. And so as you're building a system, you decide that what you want to do is just give each of those operations a different code path per entity, right? So you end up with a grid like this that you kind of need to maintain somehow, of the operations and the entities each getting their own code path. Now, if you decide to use a switch to implement this system, then what's going to happen is you're going to group all of that code together according to operations. You're going to say there's one place where I define the update function, and it's going to have a switch that references each type of entity and puts in the code path for that entity's update. The nice thing about a system like this is that if you ever change one of those operations, change their signature or add a new one, then the places you have to visit in the code are one, that it's all grouped together. But when you add new entities or change the properties of any of the existing entities, now the stuff about each entity is spread out throughout the code. Vtables, of course, just gives you the opposite organization. It groups things by the entities. So now the variables for your entities and the code paths for the update and draw for the player can all be together, and the same things again can be together for each of the other types of entities. But this creates a much more painful problem when you want to change the signature, because now if I add or remove a parameter or a return type to one of those functions, suddenly I have lots of places I have to visit, right? So you really only get to pick one of these two ways to organize your code. And once you've picked it, changing your mind is going to be pretty costly. But what's worse than that is the one you pick now isn't just about how you organize your code. You're also being forced to organize your code in a way that is coupled to the code that gets generated by a compiler. So you might not even get to pick the ideal organization for the code gen properties that you wanted, right? So that's a quick look at the problem, but what can we do about it? Basically, our idea here is that we need to do a little bit more work to make the user interfaces decoupled from the program representation, right? Right now, when you have a text file, it has a particular order, and that order that the code gets laid out is the user interface that the user gets to deal with for modifying their code. And we think that while we are working on changing the format of code, this is another problem that we have a pretty good opportunity to make progress on. And we've done a little bit of this so far, and Ryan's going to show you what we found.
So Alan went through a number of problems where it feels like they shouldn't actually be that important, but they turn out to be, and for various reasons. And one of those is, indentation and brace style. So, braces are one of those things where people kind of like to, argue about them. I've probably argued about them. You've probably argued about them. Everybody kind of, there's a lot of good discussions about braces, but We took a look at the problem and we thought that it actually didn't have anything to do with storing the code. So the braces that you see on screen right now are actually just a detail about how the code is rendered. So if I wanted to change which line, for example, the braces are on, that's pretty easy. It's just a slightly different code path in the renderer for the code, and the code just updates. Nothing actually changes about the code structure, but we just render it slightly differently. Additionally, since we're in the position to be making these decisions, we can just turn off braces altogether. In fact, within a system like this, there's no reason why they should really be there anyways, so we can just turn them off entirely. Additionally, I've prepared this little window for this demo, which allows me to adjust the indentation scale. So that's just kind of another detail about how the code is rendered. So if you like to write with no indentation, you can do that. Or if you like to write with extremely wide indentation, you can also do that. Point is, it's just a user setting. There's nothing that has to change in the code about it because it's just a detail of the rendering. Additionally, another thing that you may see in IDEs, for example, is the ability to collapse code sections, often referred to as code folding. In Dion, we've made a feature that kind of replaces this, and we're pretty happy with it, which is we call it code level of detail. So if I wanted to get a high-level representation of all the code that's kind of in this view right now, I can actually just zoom out, and all the details will collapse, and I can sort of zoom in and out just using my mouse wheel here. To kind of adjust the level of detail at which I'm viewing the code. And that was pretty easy to implement within the system because, again, we're just doing a render pass over a tree, so we can just selectively decide to choose not to render certain levels of the tree, and then you get something like this. Additionally, the most important problem probably that Alan talked about was the idea of code organization and the impacts that can have not only on your workflow, but also on code that gets generated. And in Dion, because we're kind of in control of how the code gets rendered, we're in a pretty good position to actually pick a subset of a code base to render next to each other. So this is the global view. You may have seen this in the corner here. It says global view. And a feature that we've implemented to start addressing this problem of organization is something we call slices. So I have a slice here. It's called vector math, for example, and it has all of the vector math stuff that we have in this little demo file that we've prepared. So I can actually right-click on this thing and click View as Slice, and it'll actually just take me to a code view that shows me all the stuff that's in that slice, and I can actually still perform edits here because again, it's just choosing the things to render to me. It's a code view just like anything else. And I can exit out of this and come back to the global view as well. Additionally, if I wanted to see all the entry points in the demo file, I could actually just view that as a slice too. And here we are. Here's all the entry points. Again, just like a regular code view, I can still zoom out and make edits to the code just like normal, and all of the changes will stay. So it provides a new way to sort of organize your code and have things show up in organizations that fit the workflows that you're dealing with at any particular point in time. So if I wanted to make one of these slices, like for example, if I didn't want to see all vector math stuff, but only the vector math stuff for four-dimensional vectors, I could do that too. I could say like vector 4D slice, and I can make that an unstructured set. That's the way we store these. And I could just start putting in all of the stuff that I want to see inside of this slice. So I could say vector 4D, the type, I want to see the constructor, I want to see the print vector 4D function. And now I have a slice, and now I can view that as a slice, and here's all the code that's in that slice. So that's sort of what we've got so far when it comes to code representation, but there's plenty of other stuff to do as well. So for example, I've put 4 examples on the screen here. On the right-hand side, we have a few mockups, one of which is using actual UI for literals. That's maybe a little bit better suited to the data that you're manipulating. So that example is a color picker for a 3D vector. We could also start showing lower-level details about the code. So for example, showing the actual byte layout of a struct. so you don't have to reason about what that might look like in your head, just looking at the textual code. And additionally, we could imagine executing code inside of the editor to form custom UIs. There's just a lot more we could do. We're also thinking about organizing code in more higher level structures like tables, for example, like the table that Alan showed you. There's not much reason why we couldn't just visualize code that way. So there's a lot more we could do, and we're kind of just scratching the surface. But that's all we've got for you for this subject, so we're going to move on now.
All right, so we've introduced you to the few problems that we've found that we could actually make progress on. We spent a lot of time working on, a lot of problems and, toying with different ideas for solving them, and those are kind of the best nuggets we have so far. This last section, what we're going to do is just take a look at some of the hardest problems that current systems try to solve and show you that really what made all of these hard are kind of the things we've made a little bit of progress on, and that we think we can start to do a better job using a system like the one that we're talking about building. So on the screen here, we have two refactoring menus from Visual Studio. The different refactoring options are available in different contexts, so you get, little bits here and little bits there. But overall, these are kind of underwhelming in our opinion. Rename, something we've already showed you we can do fairly easily. Create a declaration, extract function. Some of these are actual code transformations, and some of them just help manage boilerplate. There's also tools that go a little bit farther than those sort of basic built-in things in Visual Studio. Here is a couple of screenshots from a C++ and Java version of JetBrains, the ReSharper tool. So again, you can see that there's, a menu of options, and some of them, you could imagine being pretty useful, but a lot of them are just for managing boilerplate. And we think that when you don't have to deal with the fact that errors could get in the way, when you don't have to deal with the fact that the type information and the structure of the code is hidden from you, and when you have freedom to create new UIs that better suit the kinds of manipulations you want to do, that you could make much, much better systems than just these things we have so far. And so we've only gotten to barely start doing that, but Ryan has a demo of a few things that we've been able to do to show you what that looks like in our system.
So to demo a few of the code transformation features that we've started implementing, first I just want to introduce an enum here. I'm just going to call it my test enum, and I'm just going to put a few constants into this thing. So I'm just going to say like foo, bar, baz, and then I'm going to make a procedure that talks about this test enum. So I'm going to say my procedure, for lack of a better name, and inside of this procedure, I'm going to have a value, which is going to be one of these test enum things. And something you often want to do with enum values like this is switch on them, right? So I can switch on the value. And at this point, this enum isn't particularly large, so it's not necessarily that interesting to show this. Maybe I can add like a few more here just to make it a little bit more slightly more interesting. So, if I were to form a switch statement for this thing, I'd have to go through and make a separate case thing for every single one. And we just don't think that kind of work is actually worth it. So what we can actually do is something we call a transformative copy-paste. Instead of a regular copy, so if I just did a regular copy, it'd give me that. That's not really that useful. What I want instead is to make case labels for all of these. So I'm going to do a transformative copy paste. Whoops, did I mess it up? Okay, there we go. So now we have all these case labels, and they were just automatically generated from the transformative copy paste. That's one example of a more naturally integrated refactoring operation that we're able to do fairly easily. So instead of just a regular copy-paste, we do a copy-paste with some transform, and that transform is a lot easier to write, we find. Additionally, something else we can do is just pull variables out as parameters to functions, and just still have them work, have all the references still work, and that all works out pretty well there. Additionally, we can do more than that. So for example, here's this print data function. It takes a pointer and also a size. And, maybe if you find yourself using the pattern of pointer and size a lot, you could actually want to you might want to extract that out as a struct. So what we can actually do here is pull parameters out as a struct, and you'll see that we have a struct here. Maybe I want to rename this to be data, and you can see that the actual print data function here is it correctly had an accessor to the struct that was passed to the function inserted in all the usage sites of the two parameters, and that all just this just keeps working. So that's kind of what we've got so far. It's kind of worth noting as well that some of the refactoring features that are often present in IDE UIs, for example, just kind of fall naturally out of the system. So we have renaming, which I've already demoed to you, and there's also a more subtle one, which is has to do with copy paste as it normally is. So if I had a struct here, I could imagine having inside of this function parameter list, I could imagine having a few declarations, like a couple of I32s here. If I copied and pasted this normally in text, I would have to go and remove the commas and add new lines and everything. Within Dion, it just pastes normally because the information being copied has nothing to do with commas. It only has to do with the actual semantic information that's being copied and selected with my cursor here. So I can copy and paste that, and there's no commas to fix up or anything. It just pastes in the semantic content, and then that is rendered however it needs to be. We're pretty encouraged by this. We didn't get to implementing as many refactoring operations as you could imagine, but we're pretty encouraged because of the fact that the code is so small to actually implement these. And it's small because it's much easier to do semantic transformations to code because we're working with semantic data instead of text. So, you can see the line counts for these features, 80 lines of code max, and many others that are kind of just free. And we think that these are even higher than they should be. We think that they can actually get a little bit lower. And of course, there's plenty more to do. You can imagine making your own code transformations with your own code. There's plenty of stuff to explore when it comes to tree-based pattern matching and replacing. And of course, we've already talked about alternate perspectives of code, like tables, for example. Doing refactoring operations on those would be potentially very powerful. So there's plenty more to do. Again, we're just scratching the surface. We're 8 months in, but that's what we've got so far, and we're pretty excited about it.
So, before I talk about what this slide represents, I just want to say that when we started this whole thing off, we didn't really know what we were doing. We just had some ideas that we wanted to explore that required us to question some fundamental assumptions and maybe open up some previous decisions that had already been made about how our systems would work and explore alternatives. And we think that the Handmade community is a great place because of the fact that it has encouraged that kind of thinking. And because we went and chased down that idea, we ended up thinking about programming in the way that this diagram describes. So what we have here in this diagram is a programmer on the left side and a computer on the right side, and the interaction that happens between them. The interaction that we would like to happen between them as well as possible, right? The programmer sends some intention into the computer one way or another, and then the computer tries to do a computation for that matches the intention and then sends back a result. And the better we can make the cycle work, the happier the programmer will be. That's the new theory that we got by working on this project. So, we've tried a lot of ideas. Some of them were kind of dead ends, and a few of them were sort of the things we've been able to show you today. And we think that it has shown us a path to making a much better version of this wheel that we sat down to reinvent. But, there's also so much more that we haven't got a chance to look at. And this is just one place where we found some assumptions that were a part of the system we were working with. So if we are going to leave you with one thought, it's what are the wheels in your life that you are currently taking for granted, and how would you reinvent those wheels?
So that's it for our talk, and we want to give a few acknowledgments out to three people or groups that were very influential for this project and for us. First is Casey Muratori, who not only started the Handmade Hero series, which kind of sparked the Handmade community. He also gave us some pretty useful feedback. Seemed like small feedback at the time, but it grew to really change the way we thought about the project, and I think the project's turned out for the better because of it. Additionally, we have to thank Abner for inviting us. It's amazing to have a Handmade conference, and it's even better to be invited to it. So thank you so much for inviting us, Abner. And of course, we have to thank the Handmade community. We're only tackling one side of the wheel. There's lots more to reinvent and to improve. Word is there's going to be a teaser following our presentation about tackling another side of the wheel that we take for granted and we think can be improved. So we encourage you to stick around for that. There's plenty of other great work happening inside of the community, and it's always great to share and be inspired by everything that everybody's doing. So thank you to those three people and groups. And of course, thank you to everybody who tuned in for our talk. If you'd like to follow what we're doing, you can go to dion.systems, team at dion.systems, or follow us on Twitter at dion.systems. And there's personal names and Twitter handles as well for Alan and I. And we also have a third team member who didn't present with us, but he's been a huge help. And he's on the slide. His name is Miguel Lechon, and his Twitter handle is Debiaton. And yeah, so that's it. Thanks everybody for tuning in. And I believe we'll be moving to a brief Q&A.